In this lecture, we will discuss the notions of ordered pair and Cartesian product. And by way of example, we'll construct a proof that involves a Cartesian product. Recall that we have introduced set notation to group objects together. So for instance, we can group the elements 1 and 2 together in a set by listing them and enclosing them in curly brackets. By our interpretation of the curly bracket notation, there is no order imposed on the elements of a set. The set containing the numbers 1 and 2 is equal to the set containing the numbers 2 and 1. Sometimes we do want to impose an order on the elements of a set. Think, for instance, of a coordinate denoting a point in a two-dimensional graph. The first element of the coordinate that typically refers to the x-axis, the second coordinate refers to the y-axis, and we do not want to interchange these two. For such cases, we introduce some new notation. We'll denote the ordered pair with first element A and second element B by listing these two elements A and B and enclosing the list in parentheses. The ordered pair consisting of the numbers 1, 2 should be distinguished now from the ordered pair consisting of the numbers 2, 1. We officially record that the order of the elements of an ordered pair is important by means of the following property of pairing. The formula stating that two pairs are equal is logically equivalent to the formula stating that the first elements of the pairs are equal and the second elements of the pairs are equal. It's convenient to have a notation for the set of all ordered pairs that we can make by taking the first element from some set A and the second element from some set B. The set of all such ordered pairs is called the Cartesian product of A and B, and it is denoted by A times B. Let's consider a few examples. The Cartesian product of a set consisting of 2 elements and a set consisting of 3 elements consists of 6 ordered pairs. The first 3 have as first element 0, the second 3 have as first element 1. The Cartesian product of the set of natural numbers and the set of integers consists of all pairs of which the first element is a natural number and the second element is an integer. To emphasize that the order in which we list the elements of an ordered pair is important, note that the pair 3, minus 2 is an element of this Cartesian product because 3 is a natural number and minus 2 is an integer, but minus 2, 3 is not an element of this Cartesian product because minus 2 is not a natural number. It's convenient to introduce some shorthand notation for Cartesian products in which all elements are taken from the same set. We denote by A squared the Cartesian product of A with itself, and so the set of all pairs. By A cubed, we denote the set of all triples that we can make by taking the elements from some set A, etc. We also formulate a property for the Cartesian product of two sets A and B. The formula stating that a pair is an element of this Cartesian product is logically equivalent to the formula stating that the first element of the pair is an element of A and the second is an element of B. Let's work out an example involving the notion of Cartesian product. We shall prove that whenever A is a subset of B, then the Cartesian product of A with itself is a subset of the Cartesian product of A with B for all sets A and B. We shall first construct a derivation and then transform the derivation into a mathematical style proof. The formula is an implication, so we start by applying the implication introduction rule to simplify our goal. We get the inclusion of A in B as an assumption and should still establish that the Cartesian product of A with itself is included in the Cartesian product of A with B. Our goal is to prove that some set is included in some other set, so we apply the definition of inclusion. Our new goal is then to prove that every element of the left-hand side set is included in the right-hand side set. Note how we take into account that the elements of a Cartesian product are pairs. Since our new goal is a universal quantification, we apply the universal quantification introduction rule. Declaring an arbitrary element of the Cartesian product of A with itself and stating as our new goal that it is also an element of the Cartesian product of A with B. By the property of Cartesian product, to show that the pair x, y is an element of the Cartesian product of A and B, it suffices to establish that x is in A and y is in B. We now switch to forward reasoning mode. Again, by the property of Cartesian product, from the assumption that the pair x, y is an element of the Cartesian product of A with itself, it follows that x and y are both in A. We apply conjunction elimination to get both conjuncts as separate formulas. Next, by the property of inclusion, we can use the assumption that A is a subset of B, which is still valid, to conclude from y in A that y is also an element of B. And then, with an application of conjunction introduction, our derivation is complete. We shall now transform our complete derivation into a more readable mathematical style proof. The mathematical style proof starts with stating the main goal of the proof, which is to prove that if A is included in B, then the Cartesian product of A with itself is also included in the Cartesian product of A with B. Then, an implicit implication introduction is applied to get a simplified goal, while generating an assumption. Note the word suppose. The proof proceeds with an application of the definition of inclusion, which allows us to replace the inclusion to be proved by the formula that serves as its definition. Then an implicit universal quantification introduction is applied, with the declaration of a pair x, y in the Cartesian product of A with itself. Note the word let, which introduces the declaration. For this pair, we should now establish that it is an element of the Cartesian product of A with B. An application of the property of Cartesian product allows us to conclude that both the first and the second element of the pair are elements of A. Now we can finish the proof. First, we combine the fact that A is included in B, which was stated as an assumption earlier in the proof and is still valid, and the fact that y is in A to conclude by the property of inclusion that y is in B. Then, we combine the facts that x is in A and y is in B to conclude by the property of Cartesian product that the pair x, y is in the Cartesian product of A with B. The proof is now complete. We have not assumed anything particular about the sets A and B, so we have now established that for all sets A and B, if A is included in B, then the Cartesian product of A with itself is included in the Cartesian product of A with B. Let us emphasize again the importance of notation in the context of set theory. When we write the numbers 0 and 1 separated by a comma, then we are just listing two numbers. If we want to form a pair of these numbers and find the order in which we list the numbers important, then we enclose the list in parentheses. If we want to group them together but do not care about the order in which they are listed, we put curly brackets, and then we form a set containing these two numbers. This concludes our discussion of pairing and Cartesian product, and it also concludes our discussion of the key notions of set theory. Next, we shall discuss relations.